In the next 4 minutes, a single wrong decision will destroy $200,000 worth of molten glass. The furnace operator doesn't know it yet. The temperature gauge reads normal. But 50 degrees below the surface, the glass isn't melting uniformly. By the time sensors detect the problem, it's already too late. The entire batch is ruined. This happens in glass recycling facilities more often than you think. And it's just one of 5 critical decisions that determine whether millions of bottles become premium products or expensive waste. Today, we're going inside the factory to show you exactly where these decisions happen, why they matter, and what happens when they go wrong. Glass recycling is one of the most efficient industrial recycling processes in existence. Unlike plastic, glass can be recycled infinitely without losing quality or purity. But this doesn't mean the process is simple. A modern glass recycling facility processes between 200 and 400 tons of material every single day. That's roughly 1.5 million bottles in a 24-hour cycle. This is high-volume manufacturing at industrial scale, where every second counts and every decision has massive consequences. The challenge isn't just melting old glass. It's about making critical process decisions that balance speed versus safety, manufacturing, energy consumption, and final product quality. One mistake, and you don't just lose one bottle. You lose entire production runs. This is advanced manufacturing, where industrial engineering meets industrial risk management. The factory must decide, how pure does the material need to be? How hot should the furnace run? When is automation better than human control? These aren't simple questions. They're engineering trade-offs that define the entire industrial workflow. The glass recycling process follows a precise manufacturing step-by-step sequence. Let me break it down. Step 1. Collection and sorting trucks deliver mixed glass to the facility. Bottles arrive in every color: clear, green, brown, blue. They're dirty, broken, and mixed with caps, labels, and sometimes even ceramics or stones. The first critical decision happens immediately: automated factory systems or manual sorting. Most modern industrial plants use optical sensors combined with human oversight. Why? Because this determines quality from the very start. Step 2. Contamination removal. This is where hidden industrial decisions become critical. Metal caps, plastic labels, ceramic pieces, all of these must be removed. Even a tiny piece of ceramic can create defects in the final product because it doesn't melt at the same temperature as glass. Here's a real example. In 2019, a European facility lost an entire week's production because a single porcelain plate fragment made it through sorting. The ceramic didn't melt in the furnace. Instead, it created thousands of microscopic stones throughout the molten glass. Every bottle produced that day had to be scrapped. Cost: over 400,000 euros. Magnetic separators pull out metals. Air jets blow away paper and plastic. The tolerance limits decision here is strict. Less than 0.5% contamination allowed. Above that, the entire batch gets rejected. Step 3. Crushing and grinding. Clean glass enters industrial crushers. The goal is to create what the industry calls cullet, small, uniform glass fragments. But here's the critical point. Particle size matters. Too large, and the furnace can't melt it evenly. Too small, and you create dust that affects worker safety and clogs equipment. Engineers must choose the exact crushing parameters based on furnace capacity and production speed. Step 4. Secondary cleaning and color separation. Even after crushing, contaminants remain. Advanced manufacturing systems use water baths, vibrating screens, and laser scanners to achieve material purity above 99%. Color separation is another process optimization challenge. Mixed colors create lower-grade glass. Separated colors maintain premium quality. The factory must decide: invest time in perfect separation or accept lower market value. Now we reach the heart of the factory process. This is where industrial decision-making separates successful facilities from failures. Critical decision number 1. Furnace temperature control. The melting furnace operates between 1,400 and 1,600 degrees Celsius. This is not a suggestion. This is a no margin for error requirement. Why this step matters. If the temperature drops even 50 degrees, the glass doesn't fully melt. You get solid chunks mixed with liquid. The entire batch is ruined. But if temperature rises too high, you waste massive amounts of energy and risk damaging the furnace lining, which costs millions to repair. This mistake ruins everything. So how do factories control it? Modern smart factory systems use real-time temperature sensors at multiple points inside the furnace. Industrial safety systems monitor constantly. If readings drift outside tolerance, automated controls adjust fuel flow within seconds. But even with automation, disasters happen. In 2020, a sensor calibration error at an Asian facility went undetected for 6 hours. The furnace was running 80 degrees too cool. The glass appeared to melt, but it retained solid particles throughout. By the time engineers discovered the problem, they had produced 50 tons of defective cullet. The entire batch had to be discarded and reprocessed. Loss: over $180,000, plus 2 days of halted production. Here's the engineering trade-off. Faster heating means higher energy consumption. Slower heating risks production delays. The factory must balance cost versus efficiency every single hour. Critical decision number 2, cullet to raw material ratio. Here's something most people never consider. Recycled glass isn't melted alone. It's mixed with raw materials like sand, soda ash, and limestone. The critical step in manufacturing is deciding the ratio. More cullet means less energy needed because recycled glass melts at lower temperatures than raw materials. But 100% cullet creates process control challenges because you need some virgin material to control viscosity and chemistry. Most industrial production uses 20% to 50% cullet. The exact percentage? That's an irreversible process decision made based on furnace design, product type, and quality requirements. One wrong decision here affects energy bills, melting time, and glass quality. Engineers must calculate this daily based on cullet purity and furnace conditions. Critical decision number 3. Forming method selection. Once glass is molten, it must be shaped. The factory has 2 main options: blow molding or press molding. This determines quality and production speed. Blow molding creates lighter bottles with thinner walls. Press molding makes thicker, more durable containers. Industrial engineering teams analyze product requirements before choosing. A wine bottle needs different specifications than a medicine bottle. Speed versus safety manufacturing principles apply. Faster production might compromise wall thickness uniformity. Automated factory systems control the forming process, but the initial decision about method and parameters is purely human. Critical decision number 4, cooling rate, annealing. This is where defect prevention becomes critical. Fresh glass bottles exit the furnace at over 600 degrees Celsius. Cool them too fast, and internal stress creates cracks. Cool them too slow, and production bottlenecks occur. The annealing process must follow precise temperature curves. Industrial workflow requires bottles to pass through an annealing layer, a specialized cooling tunnel, for exactly the right amount of time. What happens if this fails? In 2021, a North American facility rushed their cooling process to meet a holiday season deadline. The bottles looked flawless coming off the line. Quality control approved them. They were packaged, shipped, and filled with carbonated beverages at the customer's facility. Then, 3 days later, thousands of bottles began exploding on store shelves. The internal stress from improper annealing had created invisible fractures. The cost of the recall exceeded $2 million, not counting the damage to reputation. This is why quality control inspection happens immediately after annealing using polarized light. Stress glass shows visible patterns under polarization. Inspectors reject entire batches if defects exceed 2%. It's expensive to reject product, but it's catastrophic to ship defective product. Critical decision number 5. Quality versus cost decision. Every mega factory faces this dilemma. How much testing is enough? Full inspection means checking every bottle for defects, cracks, bubbles, dimension accuracy, wall thickness. This guarantees quality but slows production and increases labor costs. Statistical sampling is faster and cheaper, but carries risk. If a defective batch passes through, it reaches customers. Here's where this decision gets real. A South American facility once switched from 100% automated inspection to statistical sampling to cut costs by 15%. Within 3 months, a batch of bottles with microscopic cracks made it to a soft drink manufacturer. The bottles failed during the pressurized filling process, causing equipment damage and production line shutdowns at the customer's plant. The glass facility lost the contract entirely. Annual value: $3.5 million. Most modern industrial plants now use hybrid systems. Automated sensors check 100% for critical defects like cracks, while human inspectors sample check dimensional accuracy and appearance. This industrial risk management decision defines the factory's reputation and profitability. Saving money on inspection can cost you everything. Inside the factory, process efficiency depends entirely on measurement and control. Because, as we've seen, the cost of failure is measured in hundreds of thousands of dollars, lost contracts, and destroyed reputations. Real-time monitoring systems, advanced sensors, track everything. Furnace temperature at 12 different points, pressure control informing machines, viscosity of molten glass, cooling rates in the annealing layer, production speed on conveyor systems, data flows to central control rooms where engineers monitor industrial workflow in real time. If any parameter drifts outside tolerance limits, alarms trigger immediately. This is industrial safety systems working to prevent failure consequences before they happen. Prevention costs thousands. Fixing mistakes costs millions. Ignoring the warning signs? That can cost you the entire business. Testing protocols before bottles leave the facility. They undergo multiple tests. Thermal shock testing. Bottles are rapidly heated and cooled to ensure annealing worked correctly. Pressure testing. Compressed air is pumped inside to verify wall strength. Dimension verification. Laser scanners check height, diameter, and neck specifications to ensure compatibility with filling equipment. Visual inspection. Both automated cameras and human eyes check for bubbles, stones, and surface defects. Failure rate in well-managed facilities is below 1%. That might sound small, but at industrial scale, that's still 15,000 rejected bottles per day from a facility processing 1.5 million units. Energy management. Glass manufacturing is energy intensive. Furnaces run 24/7 because stopping and restarting costs more than continuous operation. Process optimization includes heat recovery systems. Exhaust gases from the furnace preheat incoming air. This reduces energy consumption by up to 30%. Engineers must choose: invest in expensive heat recovery equipment or accept higher operating costs. This eco-industrial process decision affects both profitability and environmental impact. After all these critical decisions, clean molten glass becomes new bottles in roughly 24 hours from entry to exit. The connection between decisions and results is absolute. That temperature-controlled decision in the furnace? It determines whether glass has the right viscosity for forming. The cooling rate choice? It decides whether bottles can withstand the pressure of carbonated beverages. Every single critical step in manufacturing affects the final product. Skip contamination removal, and ceramic particles create weak points. Rush the annealing process, and bottles crack during transport. This is sustainable manufacturing at its finest. Recycled glass uses 30% less energy than making new glass from raw materials. It reduces carbon emissions and preserves natural resources. The circular economy process works because of precise industrial decision making at every stage. Nothing is left to chance. Nothing is approximate. Modern industrial plants achieve remarkable efficiency. 90% of collected glass becomes new products. The remaining 10% is either too contaminated or becomes aggregate for construction materials. A single recycling facility prevents thousands of tons of waste from reaching landfills annually. But this environmental benefit only happens because of rigorous waste to raw material processing standards. The bottles produced from recycled materials are chemically identical to bottles made from virgin materials. same strength, same clarity, same durability. Customers cannot tell the difference because, scientifically, there is no difference. The glass recycling process reveals something profound about industrial manufacturing. Success isn't about one brilliant innovation. It's about thousands of correct decisions executed precisely every single day. From that initial sorting decision to the final quality inspection, each choice cascades through the entire factory process. Engineers don't have the luxury of approximation. Industrial production at this scale demands absolute accuracy. We've seen what happens when those decisions go wrong. A ceramic fragment costs 400,000 euros. A sensor error destroys 50 tons of product. Rushed cooling leads to a $2 million recall. Poor quality control loses a $3.5 million contract. But when decisions are made correctly, something remarkable happens. Temperature stays precise. Timing remains exact. Quality standards hold unwavering. And millions of glass bottles complete their journey from waste back to resource. This is why factories invest millions in industrial safety systems, real-time monitoring, and automated quality control. The cost of prevention is always lower than the cost of failure. Always. The next time you recycle a glass bottle, remember, it's not just being melted down. It's entering a sophisticated industrial workflow where critical process decisions transform waste into a resource, where engineering trade-offs balance efficiency, quality, and sustainability, where one wrong decision can indeed ruin everything, but thousands of correct decisions create something remarkable. That's the reality inside the factory. That's how millions of glass bottles are recycled every single day. And that's why every single decision matters.